Well, it's great to be here with you today,
Thank
Anca.
you, Eric.
And I've been learning about your work since we started talking a couple of years ago, and I'm very impressed with how deeply it resonates with some of the big themes at Microsoft Research. And
That's why it's so lovely to be here, because there's a lot of connection between the stuff that I care about and the work that you all have been doing. It seems like you have a passion here, not for AI only, but AI in the context of society and humans, and I sense good collaboration prospects.
Well, let me ask you a
going
question.
forward.
Well, yeah, you have a deep passion about the collaboration between machine intellect and people, humans, and broader societal implications in their uses of AI. How did that get started? How did your interest get going in that space?
Yeah, so I did my PhD at CMU in the Robotics Institute.
Who's your advisor there?
Sid Srinivasa, who's now at UW in Seattle. So he was running primarily a manipulation lab, robots in kitchens, picking up stuff, actually getting robots to use their arms and their hands to do things in the physical world. And I joined this lab, and we were part of the Quality of Life Technology Institute.
Great phrase. I love
Quality
that.
of life, yeah. So it's empowering people to live independently in their home for longer was part of the mission.
So aging in place kind
Aging
of thing.
in place, and but we were in a manipulation lab, and so I started. I had the background in optimization. I always loved optimization. I still do optimization, but
Do you remember I have to say this. I remember like the afternoon where we learned about differentiation and setting the second derivative to x and the first derivative to y, and saying, "Oh my God, we can optimize a function." I remember like in like middle school being so excited about that.
So I have two skills. One of them is taking gradients. The other one is applying Bayes' rule. That's all I know how to do. Those are the two things that I do.
But you know, if you know those two things, I think you're set for almost anything.
I build a career on modeling people as doing Bayes' rule and optimization, and on getting robots to do Bayes' rule and optimization about people.
Bayes' rule and optimization. That's kind of like the whiteboard for AI. Yeah, that's your pens and your whiteboard. Now go.
Now go, yeah. So how did I get into it? Well, I was working on motion planning and for manipulation, and I started wondering how that fits in the context of, okay, we want this robot to be in a kitchen, motion planning, that's great, but aren't there going to be people in that kitchen? Do we want them to leave the kitchen when the robot is preparing them a meal? Or should they be able to, stick around and be assisted, helped by the robot, empowered to do the things that they would normally do
You want to see somebody
in their daily
full
lives?
of bruises, and then they come tell you that, they got too close during the peanut butter and jelly assembly process.
Or scared off or whatnot. And so we started thinking about what does it mean? How does the problem definition for motion planning itself change from this very functional one? I have a goal, I have to be efficient, maybe, and I have to avoid obstacles, I have to avoid collisions. That was the definition. How does it change the moment the robot does not operate in isolation anymore? And something sort of clicked at that point for me, because we started thinking about, okay, we have a new problem definition. We have to integrate some notion of human state, at least a human observer, if not a collaborator, at least a human observer into this mix. What does that mean? And that was the birth of my thesis, which we called legible robot motion planning. And it was Bayes' rule. It was this notion that the moment you have an observer, that observer is making inferences about what the robot might do next. And that it's not just important for the robot to do its task, reach its goal, but it's important for it to do so in a way that also enables the observer to figure out what's going on. Now, how do you so we wanted intent expression. We wanted functionality together with intent expression. And intent expression was a very fuzzy concept, but what we managed to do, again, because I only know two things, we said, well, people probably expect the robot to be doing some form of argmax because it's a robot. So that's a pretty reasonable assumption. And then we said, okay, when they see the robot moving, they're probably interpreting its motion as evidence about what it is that the robot is trying to do. And there came in Bayes' rule. So we had a Bayes filter running over this. And that was our very simple model of how humans might be interpreting robot motion. And then the robot could actually be optimizing to express intent. That was the story.
Well, it's a great story, very expressive. I do think that sometimes just integrating some foundational structure, data structures, variables, dependencies, inferences about people in what was earlier a standalone optimization without consideration of people opens up such a rich space for deep technical work. And what makes it really exciting is the link to psychology in humans. I mean, I'm assuming that we'll completely resonate on this. I did something very similar at the NASA Mission Control Center once, and it just lights up a whole area and raises so many questions. For example, what do people think about goals? How do they represent them? How do you even represent what people think about goals in your optimization?
Right.
And so the uncertainty about that.
Right, and so the way I started seeing it over the years was first this notion of, okay, I'm not going to draw the box around just the robot and the actions and the physical environment, right? Now, and because that's what we typically think about AI, and then there's a reward function exogenously falling from the sky. Let's start drawing the box around the person too, right? And so now we're operating this dynamical system where at the very least, human state, and not just physical state, but maybe internal state, right? Their goals or what they think about the robot, that becomes part of this dynamical system that we need to be doing control over.
Exactly.
And then it became a little more complicated than even that. Recently, we've started almost on a rabbit hole to realize that, okay, thinking about this as a dynamical system with human internal state is one thing, because then the robot can think about making predictions about the human state, even making predictions about how its own actions might influence human state, how it might guide people to take certain actions and help them in the task that they're trying to do. But then it became a little more complicated because it turns out that sometimes people also think about the robot and try to influence the robot. And so it becomes very quickly a game theoretic setting. We've been digging into that recently. So an example that I work with cars a lot these days. I still work with manipulator arms, but I also work with cars. And an example that I like to give is sort of, with cars, you cannot get away without incorporating human state into the picture, right? Because there's all these people around. So you have to start making, at the very least, predictions about where these people might be going and avoid collisions with them. So get out of their way. And that's a first pass. But then it becomes more complicated because...
You mean you being the automatic car?
You mean the automatic car. And then it becomes more complicated because you... end up, if you do this, you realize that in sort of high traffic, crowded situations, if all you do is anticipate where people go and make sure you're out of the way, at some point you can get stuck. Like at a four-way stops, people keep inching forward and then you're stuck there because you keep on anticipating that they'll go and you stay out of their way. Or in high traffic situation, you try to change a lane. It's hard because people keep on coming and there's not enough of a gap in traffic. And so that's difficult. And then you have to start, as a car, as the autonomous car, you have to start reasoning about how you might actually be able to influence these predictions that you're making, right? That you have some level of control over that.
Even the manners you display. Well, I'm a little bit rushed and punchy. I'll basically make it clear that I think I got to the stop sign in a four-way first.
Yeah.
I'll make it clear. It's like, Bye.
Me, yes.
Me.
Inch forward, go.
There's lots of communication, micro communication that goes on there.
That's right, and it's through this almost like a bad body language of the car. And so the reason I was saying it becomes game theoretical is because not only you have to reason about your influence on other people, which is, for example, the fact that they will likely slow down if you go in front of them to make space for you. But then you also have to be ready for the other side, the fact that people might try to influence you, and that is the example of someone might actually, when they see you come in, start accelerating to deter you from going in front of them. So as an autonomous car, yes, you have to be clear about what you want to do so that people can respond. You also have to be ready for people responding, non-collaboratively. They don't always respond collaboratively.
Yeah.
And so there's this mutual influence that's going on, and it's really difficult for a robot to sort of wrap its head around all of this.
Let me step back a little bit about just some essential challenges here. So we have a machine. We've done our best as researchers to incorporate a bigger model that involves people and their preferences and even their understanding of what it is that I'm doing as a robotic system.
Yeah.
Let's say we don't get it right.
Right.
Our a sense for what humans either understand or believe, or their goals or their optimization function, what they're trying to do, is different than what it is. Is there a prospect for dialogue and for kind of a back and forth in a kind of a tango of understanding?
So good question. So I think of this at two levels. I want to talk about both. The first one is this notion of having uncertainty over, not assuming a fixed model, but having uncertainty over that model, right? So different people act differently. The same person might change their mind about something over time. And so I think it's important, their preferences, we don't know what people prefer. We have no idea, right? So I think it's important to deploy these robots out into the world, first of all, with a notion of uncertainty about people. Not stubbornly thinking they know what's up, but actually being able to incorporate the dialogue in the form of natural language or in the form of actions or corrections.
One comment here that in some ways it's instilling a design principle of humility in our systems versus overconfidence.
That's a very nice way of putting it. So yes, I think robots should go into this with uncertainty. As designers, we can give them a prior, right? Ideally by collecting data from a large set of people and giving them a prior going in. I think the robot's job is to be able to leverage just a little bit of data online very quickly to adjust, to put probability mass, shift probability mass around onto the sort of the hypothesis that seems to be consistent with the behavior of the human. So that's one level, right? Just being able to drive.
Okay.
Right, level one, drive next to a person and watch for what they're doing and make inferences about their goal, about their preferences, about their driving style, about whether they're gonna let you in or not. So that's level one. Level two is almost like a meta level. You can have all of this uncertainty, but if it's over the wrong space, right? If you've baked in assumptions that are actually wrong. For instance, something that bugs me a lot these days is, okay, humans have preferences. We want to be flexible about their preferences, but what if there's just something that they care about that we can't even represent? Right? Either because we've made the space of possible preferences not expressive enough, so maybe people might care about not inconveniencing others. That has to be part of something you can represent in order for you to draw inferences over that. Or it might be that people care about their robots handling their favorite mug from childhood differently. And what if the robot just has no way, using its sensors, to know that that's their favorite mug from childhood, right? That has special sentimental value. So I think we have to acknowledge that there are going to be things that are just going to be outside of our hypothesis
and it might turn out, even with an expressive representation, that some stuff is just too hard to express and the effort it would take is too much.
Right.
To limit.
Yeah, so you have to be careful. You can have expressive representations, even with these expressive, so you can have a deep neural net as your model of preferences. And that's great, except that, one, you need a lot of data from the person. Maybe you can use meta learning, maybe you can use priors. But that's still an issue. You can over-represent, you can represent too much, and you'll still under-represent, right? Because there's just going to be things that are not observable.
And then there's the idea of kind of this ambient watching and observing and trying your best as the robot, versus the robot saying, well, I'm uncertain, and doing more explicit dialogue about the preferences and goals.
And they actually act. So that's the beautiful thing about robots. I like robots because they take actions. And that means that they have this opportunity to not just be passive observers, ingesters of information. People act, people say stuff, the robot sits there and figures out what to do, but they can take what we call information gathering actions. And these can have a traditional role, right? A traditional format in machine learning where they're actual queries. Hey, human, A or B, what do you like? Or did you mean this or that? And that can be useful in resolving uncertainty. I like having robots also use their physical actions to gain information.
Did you mean this?
Right. So can it make a query, force the person to give you a correction, and see how they do something, see how they react to you. With Dorsa, I was now at Stanford. Dorsa Sadek, we did
And
this.
that's former intern with us.
Yeah, that's right. That's right. So right after she interned with you, we started working together during her
fabulous.
PhD. And so one of the projects that we did together was actually on information gathering actions over human internal state. This notion that,
Love it.
and this was for cars, right? So this is I'm driving next to a person. I don't know if they're an aggressive driver or they're paying attention or not. Or they're just a normal driver, regular nominal driver. I don't know. I have uncertainty over that. So that's that first principle. And if it turns out that if you just observe them passively, you might never know in time because they're driving in the same way regardless of, right? It's just they drive straight. So by incentivizing information gain, right? Ideally by making the robot aware of the value of information, but in a continuous state in action control setting, we sort of cheat and actually incentivize information gain explicitly. We were able to then get these behaviors through optimization to emerge where the car starts nudging towards your lane, not committing to go, but nudging towards your lane to probe you and see, will you slow down or not?
to learn.
To learn about whether it's actually safe to then go in front of you and rely on you to actually brake and make space for it.
So,
or
so,
whether
you, so,
that's
you,
not
so you're doing
unsafe.
active value of information probes, which is very interesting.
Yeah.
If you can do it safely, and
Yeah. So you'd still do this subject to all of your safety constraints. And at an intersection, she got the car to inch forward as the outcome of the optimization. So inch forward in an intersection to see if the person would slow down and let it go or not.
So it's interesting, even in that situation, the inching forward emerged as a policy, but you can imagine there wasn't even a consideration from that perspective of inching forward as communicating intention directly.
That's right.
And you can imagine doing both simultaneously.
You can imagine doing both simultaneously.
very
Yeah, and in
interesting.
that work we weren't, kind of going back to the beginning of the conversation, that work we weren't yet modeling people's beliefs about the robot's intent and reacting to that, but we were just modeling the fact that people try to be efficient, try to also be safe. We don't know what specific trade-offs they have. We don't even know if they're seeing the robot or not. But the algorithm essentially figured out that an action that will give it a lot of information is to start inching forward and then watch for the reaction.
Yeah, it's fabulous work. I think that someday this idea of assessing preferences or utility functions for robotic systems will become more popular and more assumed. I often thought that, rather than talking about what a car will do, an automated car will do, and the trades it makes, and what are the value functions, that before you can even turn on an automated system, you'd have to watch some videos in your car seat, and then set sliders as to what would you do, what are your preferences. Then when you run the car, you can assume that automated cars, when they are in autopilot mode or automated mode, that's the preference function of the driver who assessed them, which would be interesting. And then when someone else gets in the same car, like in your family, it's like all the sliders change, and it's like, now it's a new utility function.
That's right.
That could become part of our normal life.
Yeah, you go into your car dealership and there's a driving simulator there, right?
And that's where you set your parameters.
That's where you set your parameters. Because you have to be exposed to the behavior as well.
Yes,
We found.
with videos, and you can watch and then think. and then maybe a month later there's a standard check back about preferences. Yes, I'll set it again. But to understand someday that when a car on automation that's cutting you off or not letting you, not yielding properly when you're coming onto a highway, that's not the car. That's the driver, even when it's automated.
Right. Yeah, I think customizing is really interesting. And one thing that we found, this is slightly atypical work from what we typically do. This was really just, we set up a study and we wanted to see what happened. So we wrote a paper that started with the hypothesis, and the hypothesis was that people would like to be driven the way they drive. That matching the person's driving style is what cars would need to do, and we were totally wrong.
I don't feel that way when my partner, when my wife is driving.
Yeah.
She drives like me. I get really freaked out. I think so.
That's right.
I don't know if that's exactly the right.
It's exactly. I should have seen that coming, but I didn't. So we ran the study, and basically what we found is that people, when we exposed, so we did two things. We exposed them to their driving style without knowing it is theirs, as well as a more defensive and aggressive one. And then we asked them two things. One, which one they prefer, and two, which one they think is theirs. And it turns out, basically, the moral of the story is people don't want cars to drive like them. They want cars that drive more defensively. But they think they want cars to drive like them. In other words, they perceive their own.
If you ask them.
Yeah, they perceive their own style as the more defensive style. They can't actually identify their style. So they think of themselves as more defensive drivers than they actually are. And it makes sense, exactly what you were saying. If someone is as aggressive as you, well, you're not in their, my hypothesis at least, my amateur hypothesis about what's going on is that I'm in a car, if I'm the passenger, if I'm the backseat driver, I don't know that you, Eric, have seen the pedestrian and plan on stopping. So I need you to start slowing down earlier.
I see. Yeah. When you're in control, it feels like everything's kind of fluid, and
you know what you know and what you're going to do.
If you're sitting in the passenger seat, you can be very, very discomforting.
That's right.
Yeah, very interesting. Right. Let me ask you just a question about background. We often talk about the pipeline, and we see so far fewer women in our field than men, and it's always intriguing to me as to why that's the case, what's the future, how we can do better, and so that leads me to ask questions when it comes to really fabulously deep thinking women in this field who are leaders. Like, what's the background? Like, how did you first get excited about computer science and mathematics and, as you said, optimization and even Bayes' rule?
So I grew up in Romania, and I think that was an enormous luck for me because, and I stayed there all the way through high school, and I only moved for college. I went to Germany for college, but Romania is very interesting because, and this is completely anecdotal and really just a hypothesis, so take it with a grain of salt, but in Romania, if you look at the number of bachelor degrees awarded in STEM, over 50% of them go to women. And so that was a few years back. I looked at these numbers when I was in grad schools. They're a little stale. But at that time in Germany, it was something like 20-something%. So you wonder, okay, why? And my hypothesis is that it's a country in which everyone needs to be good at math from the start, right? 3rd grade, 4th grade, 5th grade. It doesn't matter if you're a girl or we don't have a lot of diversity other than gender diverse. Romania is a pretty homogenous country. We're all white, but so there's not a lot of diversity with respect to what in U.S. we think also not just about gender, but we think about underrepresented minorities more broadly. But in Romania, speaking about the gender issue, everyone needs to be good at math. And I think that's a kind of an equalizing thing. I think that you never question whether you're going to be good or bad. You just, you're going to be good because you have to.
So the idea of mathematics being critical and important for everybody.
And there are trade-offs because it comes at a cost. It's everyone appreciates math. And I kid you not, at least back when I was in high school and middle school, so I did the math Olympiad. And we were also the people who would go out and hang out and have friends and be social. Maybe this is somewhat of a skewed perspective, but I still think it's different from what happens in the US, where being good at math is almost frowned upon. And being good at sports, athletics, being the captain of the football team is what's cool.
So you're saying that mathematics was considered
was
cool.
respected. It was respected, and not necessarily. I wouldn't go as far to say considered cool, but there were a lot of there was a really good culture around it, and good groups of people, social people, also going out and having fun, and just having good relationships with other kids in class who were not also doing the math Olympiad, right? It was all, everyone was...
It does suggest that, for interventions, right, in countries where that's not the case, where we have a big disparity, that maybe thinking about what's the culture, what's community around the intellectual process would be very interesting, and equalizing things at that level.
At that level, yeah.
And then going from mathematics to getting excited about AI and computers. Well, maybe computers and then AI. I'm not sure what the direction was for you.
It was, so I got into, again, very lucky. When I was in 4th grade, we got to do some extracurriculars, and we got to choose. And my mom is really baffled because she reminds me that most of my peers chose dance, music. I chose programming. I went and learned some QBasic in 4th grade.
What kind of computer was it back then?
Pentium something.
Okay,
I don't know. Maybe a little earlier than that.
See, from my point of view, that's very modern.
So QBasic is what we learned. I would go to this little club and they would teach me QBasic, and then I actually went to a middle school, high school combo that started programming from the 5th grade. So I actually had it as part of my curriculum. And I got excited about it, so I kind of kept them side by side. It's all, for me, it's always been, math is very, very appealing, and then algorithms are really appealing too. And so putting that together, I think, has been something that...
How do you view the difference? As embodiment?
I don't, so that's a good question. I think that there's, kind of thinking about human-robot interaction, there's algorithms you can write down, and it will make the robot maybe interact with people by doing search or by figuring some things out. I think then that there's math you can write that's essentially committing to what is my representation, what is my model, what is my inductive bias that I'm going to allow myself around people. And then there's the theoretical statements that you might want to make. Not that we've done a lot of that in the realm of human-robot interaction, but we're starting to. So you want to ask questions like, I have no idea what human policies, what real people actually do, but what do I need to assume? What are sufficient conditions? What are sufficient assumptions for me to actually have a robot that can help the person?
You've jumped way to now, but back to 5th grade though.
That's right.
So you have algorithms and math.
Yeah. So I did algorithms. I did math. I tried to do Olympiads on sort of both sides, and then I read Stewart's book in 12th grade.
This is Stuart Russell's textbook with Peter Norvig,
yeah.
who, by the way, is visiting us next week.
Great. So I like to tell the story because I read this book, and it changed my world because it was just so, search and MDPs and all of that was just, somehow it clicked. Somehow I realized, because before then I thought that I wanted to be a software engineer, because that's what I knew, right? I knew how to program, and I knew about algorithms, and I thought that I would be a software engineer. And that sort of, through that book, is at the same time I discovered there's something called research, where you invent the new algorithms. And I was like, that's cool, I want to do that.
That's very cool.
And so I really loved the topics in the book, and I went to do computer science, and I tried to do research. Even in my college, I got involved with research in...
The college you went to, it was in
Germany, in Bremen, Jakobs University Bremen. And it's a little school, international, people from 100 different countries all together,
Fabulous.
this little campus. in Germany. It's a fantastic
You went
place.
right from there to CMU.
I went right from there to CMU, right? So I did 3 years of bachelor's because that's the norm in Germany. And then I went to the Robotics Institute, which again was kind of a fluke because I hadn't done robots. I had done optimization. And I thought, oh, well, but robots are pretty interesting as an application of all of this. They move in the physical world. So you write some stuff, and then instead of pixels on the screen changing, there's something in the world that happens. And that was really exciting. And even now, I mean, I like the ARM stuff, but then
When you say the arm stuff, you mean a robotic arm?
Yeah.
People here
like
haven't
that.
seen your talk yet. That might be watching the video.
That's right. I still like that, and we still do some work on that. But I've had this newer experience, which is to ride in an autonomous car, to be in a robot. That's really exciting too. So I think that's how I got there. It's a lot of luck and a lot of being exposed accidentally to the right things at the right times.
Now these days, you as we're seeing more and more, you do research at UC Berkeley. You have a team there, and then part of your time you spend in industry.
That's right.
So what's that experience like?
It's really a privileged position I feel like I'm getting the best out of both worlds. I feel like I spend my time with my students, and it's really where my core passion lies. And we get to think as forward as we want to, right? I think that's the role that we have in academia and in industrial research, right? That we don't have to make anyone money in the next 5 years, and therefore we get to think as far ahead as we want. And it's kind of our responsibility to do things that industry can't afford to do because they actually have to be building products and making things work for real. And then I only do 1 day a week, but I get to do 1 day a week in this other world of where I start seeing something that I never thought. All my stuff has been so useless until now because this whole imagine a robot would actually work, and then we actually draw the box around the human too, and think about how that changes all of our algorithms. That's what I do.
Starting with the first one, imagine if
exactly
it actually would be useful. Yeah.
So, and now with cars, it's really interesting because with cars, so I spend 1 day a week at Waymo, which is a really fantastic opportunity, and that's one of the major bottlenecks, right? If we could have cars on the road without pedestrians and cyclists and human drivers, right? I mean, perception now works well enough that it's and you can do planning and all of that. And
only if things are that simple.
Yeah, so I think it's really the bottleneck is in these interactions, this back and forth that you have to have with people, these predictions, the influence that we were talking about, all of that has to come together for you to actually be safe on the road and take your passengers to where they need to go.
So speaking about this energy and enthusiasm, let's now jump to 2045, which is basically, it's like 25 years from now.
Yeah.
Now, believe it or not, I've been at Microsoft 25 years, so I've seen so much and so much change, and it's been fabulous. It's a fabulous arc of technology and society. What's the world like in 2045? And let's start with the good parts of things. I mean, in terms of the surprises and the fun deployments of technology.
I will confess, it's really hard for me to think about this. I tend to be this curmudgeon, and I only see how things are really hard, not how things are really easy. But I think there's a lot of exciting things we can do, right? There's a lot in the space of empowering people, in the space of assisting people, in the space of, I always say that as AI systems can get better, I want us to get better as well, right? I want guidance from an AI system. I want something that takes what I want to be good at and helps me improve, helps me get better. And I think, you see that example with systems like games, right? You play Go, now you discover all these interesting moves, and so as AI can get better, it's a good time to think about, okay, how can Go players get better at Go? But I think you can bring that into the real world too, and I think you can look at all of these tasks that people might want to do, and how you might sort of gently nudge them to make progress and coach them and teach them and have them become better over time.
So a world where you're augmented and empowered
Right.
by the intellectual side as well as the robotics side potentially.
That's right.
someday.
The other thing, of course, that I remain excited about is this, going back to quality of life technology. So we're lucky so Sergey Levin and I co-advise a student, and we have these collaborators at UCSF who have taken a patient with quadriplegia and implanted, it's not quite an electrode array, but it's a neural implant. And so we're working on how we might be leveraging state-of-the-art AI techniques to empower this patient to both, my favorite, operate an arm, to do things. He wants to feed himself. That's a thing that he really
Isn't
wants
it
to do.
amazing what we take for granted?
So that's a dream of ours, to be able to do something like that. Also to be able to enable him to navigate. He has a textual interface and he moves cursors on his screen. And so,
Yeah, it's
so kind of
interesting.
getting that to be really seamless for him. And so that we'll probably make a little dent in that, but I think that's an area that could really become better and better. And I don't know if 45 or 55 or 75, I have no notion of time scales here, but you can imagine this transitioning at some point, even, dare I say it, to the rest of the population. You can imagine that you can have devices that you think stuff. You don't have to type, you think stuff, and then you get things that know what you want to do and help you with it.
It's interesting to see the rise of interest in systems, AI systems that can explain their reasoning. And in many cases, we have trouble doing that as researchers and scientists. Why is transparency or even intelligibility, why do you think that's becoming such an important thing?
I think part of the reason it has to do with calibrating trust. So it's important that people trust these systems when they're useful, but it's also important that they don't trust these systems when they're not useful. And so a large component of transparency goes back to that, right? Goes back to this notion of, okay, there's some things I'm bad at and some things I'm good at, and somehow, and I don't know as the robot what I'm good and bad at, but somehow that needs to come across to the person. One perspective that we've gotten on this has been that over time, people, if they just see enough examples, they can build up some mental model of a system's capabilities. But if they're subject matter experts, so they can tell when the thing is doing the correct thing, when not. We've been looking in ways to accelerate that process by explicitly searching for what are examples to give the person that are actually informative, right? So, okay, if you just let the system be used over time, people figure it out. But are there things that we can do to expose people to informative behaviors from the system side?
It's interesting as an early innovator in terms of maybe using too much the Tesla autopilot, to even understand and try to learn about where it wouldn't do well, beyond its own knowledge about where it would do well. In fact, it could be very confident. And I go, nope, it's not going to do well there. And I remember telling some of my colleagues, it was like learning how to drive a horse. to understand how to communicate and understand what it perceived versus what I was perceiving.
Yeah. And I think that's an example where it does seem really useful for people to very quickly get up to speed and have an accurate model of the capabilities and limitations of that kind of system. And it's really hard because, chances are it's some black box neural network. The designers themselves probably don't understand the capabilities and limitations very well, although some of the things, just given the sensors you have access to, might be inferable. But yeah, I think starting to think about, okay, what maybe you look at a policy and you look at where the policy itself thinks, so to say, that it's really important to take a particular kind of action. And maybe it presents that to you. This is something that we call critical states. It's a very, very, very simple concept. The idea is cluster these, present them to the person, and now the person gets an idea of, oh, okay, this is what you do in these situations, and this is what you think are important situations. Oh boy, this thing is missing from here. I wonder what you would do in this other state and that I don't see as you thinking is important. And sort of that, again, can be some sort of interaction where you get to query the system and build in a more accurate model over time. I think the way we've been thinking about transparency overall, it goes back to this notion of there's some. It's like robot. It's the opposite. It's robot. We talked about human internal state and how it's important for robots to understand human internal state, and how honestly people could try to be informative about their preferences, their internal state. I think the same applies to robots, right? Robots have internal state in the sense of there's stuff that the robot knows that people don't. And the robot has to understand that its actions, that people have maybe beliefs over this, they have some sort of mental model, its actions end up updating that mental model. So you have to be careful about the actions that you're taking because they're going to be shifting that mental model around. And so it's an opportunity now to take actions that are going to lead to as quickly as possible to you, Eric, knowing, okay, this is not the kind of capability that my current car or device has.
And this is getting back to the sitting in the car watching the videos or the simulator, even to understand capabilities. And
Right. And that's literally what we do. We sit people down and say, okay, here's the things that this policy finds important, and they see the thing driving, and then we see when they intervene.
Excellent.
And see that they can, hopefully we get them to intervene in states where the policy is not good and not intervene in states where the policy is good. But all work in progress.
Now, this video might be on the web, and you might look back upon it 10 years from now. So communicating to your future self 10 years from now, what's a stretch goal? You could say 10 years from now, boy, if I could do this, it'd be fabulous. What's a stretch goal to have accomplished by then, a decade from now?
Boy, everything feels like a stretch goal. We don't have to do anything.
That's a great answer, by the way. I probably feel that way, exactly the same way.
Everything.
Sometimes.
I feel that if we're not working on things that seem like stretch goals, then what are we doing, right? It's like I was saying. I feel like it's our job, and I don't claim to always be good at that. We have undergrad students that we're training, and we need to give them things that are not, maybe we can solve this in 10 years or not, but. Yeah, the real problems, they're all, for instance, this tool, right? Make an AI tool where that is almost like a decision support system for an engineer to be able to define a reward function correctly.
That's
no
a great
idea how to
goal.
do that.
Great. Well, it's been great chatting with you.
Thanks for having me, Eric.